Okay, so we're just going to take a look at some examples. And if we take a look at this first problem, we're asked to find the derivative for the hyperbolic cosine of 2x plus 3. You just want to keep in mind that when you are working out these problems, especially for our derivatives, we must be mindful of the chain rule, right? The chain rule is that outside, inside derivative. So notice that if we're working with a composition of functions, which means we have an outermost function and an innermost function, we must take the derivative for the outermost function times the derivative for the innermost function. All right, so here we're asked to find the derivative for the hyperbolic cosine of 2x plus 3. And I should make this a little bit bigger. So in order to find f prime of x, I'm going to take the derivative of the outermost function. So I'm going to leave the innermost function alone. So if I take the derivative for the outermost function, right, the derivative for the hyperbolic cosine All right, so I'm going to consult page 195 in the textbook. Right, notice that the derivative for hyperbolic cosine is hyperbolic sine. All right, so if I take the outside derivative, I'm going to have the hyperbolic sine of 2x plus 3. And this is the outside derivative times the inside derivative, right? So 2x plus 3 is my innermost function. So if I take the derivative for 2x plus 3, I have 2. And this is the inside derivative. So now if I combine the two, I have 2 times the hyperbolic sine of 2x plus 3. So if I put that in, 2 times the hyperbolic sine of 2x plus 3. All right, so pretty straightforward. Number 2 is pretty much the same, right? You're trying to find a derivative, so you would use the chain rule. Right, problem number 3. Right here again, we would use a chain rule. All right, here we have the hyperbolic tangent of 5x plus 1, and we're asked to find a derivative. So f of x is equal to the hyperbolic tangent of 5x plus 1. And we're asked to, and that should be the first derivative. So here again, there's a chain rule. We have a composition of functions. We have an outermost function, which is the hyperbolic tangent. We have an innermost function, which is linear 5x plus 1. So again, we'll use the chain rule. We'll take the derivative for the outermost function, which is hyperbolic tangent. And if we look at our formulas, notice that the derivative for a hyperbolic tangent is hyperbolic secant squared. So I'm going to take my outside derivative times my innermost derivative. Derivative with respect to x for 5x plus 1 is 5. So we have 5 times the hyperbolic secant squared of 5x plus 1. And let me just make sure I do have my secant h squared. And that was one thing I was noticing on the and that's one of the problems I found on this. It would mark some of my problems incorrect. I found these on a few of these in the homework. So notice I do have the correct response, but for whatever reason, it's marking my problem incorrect. I'm going to make sure that these things are not on the test, but I just want you to realize if you are putting in an answer that marks it incorrect, just sort of let me know and I will make the corrections on that. Okay, I've noticed in this section, there are certain problems. I think there are like 3 of them all together. Okay, and this is one of them. Okay, that it may mark incorrect, although it's a correct answer. All right, but nonetheless, in order to find a derivative, we must use the chain rule. All right, now as far as the rest of the problems are concerned, and this is one thing I have noticed. Okay, well, not the rest of the problems. Problem number 5 through 14. you're asked to find the antiderivative or the integral. You'll notice that the videos don't refer to anything about the integral. They all are videos about the derivatives for hyperbolic functions. Okay, but in this section, we're finding the derivative and the integral of hyperbolic functions. We're finding the integral and the derivative of the inverse hyperbolic functions. Okay, however, these videos only reference the derivatives of hyperbolic functions. So I just want to make sure I touch on at least one of each of these type problems. Okay, so now notice closely here we're asked to find the antiderivative or the integral. So we're going to look at the formulas for the integrals of the hyperbolic functions. Okay, so I'm going to write this down. We're given f prime of x is the hyperbolic cosine of 3x minus 3. So f of x equal to, f prime of x equals to the hyperbolic cosine of 3x plus 3. Let me just make sure that that's correct. It's 3x minus 3. And we're asked to integrate. And let me put some numbers to these. So this is number 5. All right. So I'm going to integrate the hyperbolic cosine of 3x minus 3. And remember that every integral must carry a variable of integration. All right. So if you notice in our formulas, we do have an integral formula for the hyperbolic cosine, which is so I'm going to use the other set of formulas. The integral for the hyperbolic cosine of u is equal to the hyperbolic sine of u. So I don't actually have the hyperbolic cosine of u. I have the hyperbolic cosine of 3x minus 3. So I'm going to make a substitution. I'm going to let u equal to 3x minus 3. Right? So that will allow me to write this as the integral for the hyperbolic cosine of u. However, I'm left with dx. So in order to transform dx into the du variable, I'm going to take the derivative of my substitution equation. So with my substitution equation, I'm going to take the derivative with respect to x for both sides. On the left-hand side, I have du dx. The derivative for 3x minus 3 is 3. And now I'm simply going to solve this for dx. I'm going to multiply both sides by dx, divide both sides by 3. So I have 1/3 du is equal to dx. Therefore, I can substitute dx for 1/3 du. So I have 1/3 du. Right, so everything is now in terms of u. So now I'll integrate because I have a formula to integrate the hyperbolic cosine. So I have that's equal to 1/3. The integral for the hyperbolic cosine of u is the hyperbolic sine of u. Since I don't have any limits of integration, I'm going to attach my arbitrary constant. And now I'm going to back substitute. I'm going to back substitute u for 3x minus 3. So I have 1/3 the hyperbolic sine of 3x minus 3 plus the arbitrary constant. So this is 1/3 hyperbolic sine of 3x minus 3 plus c. And well, they already gave us the plus c. All right. So you will do 6 in a similar fashion. Right, you must make a u substitution. You'll do 7 in a similar fashion. All right, find the antiderivative of the given function. All right, let's take a look at problem number 8. Right, here we're asked to find the antiderivative for this function. We're given that f prime of x is equal to 14x times the hyperbolic cosine of x squared. So here we're asked to integrate, and this is number 8. We want to integrate 14x times the hyperbolic cosine of x squared dx. All right, so the first thing I'm going to do here is I want to try to write everything in terms of the variable u, right? Because we have a formula to integrate the hyperbolic cosine of u, not the hyperbolic cosine of x squared. So my first thing I'm going to substitute is u equal to x squared. Right, so if u is equal to x squared, I'm just going to substitute u for x squared. Notice that I still have 14x, but I'm able to rewrite cosine, the hyperbolic cosine of x squared as the hyperbolic cosine of u. Right, but I'm still left with the 14x dx that we need to somehow, some way transform into the du variable. So I'm going to make a substitution. Well, we made the substitution. Now I'm going to take the derivative of my substitution equation. So just as we did before, I'm going to take the derivative with respect to x for both sides. On my left-hand side, I have du dx. On the right-hand side, I have 2x. I'm going to multiply both sides by dx. And I'm running into a slight problem. Here I have a 14x dx. And here I have a 2x dx. In order for me to make this 2x dx a 14x dx, I must multiply by 7. Remember, whatever you do to one side, you must do the exact same thing to the other side. So I'm going to multiply both sides by 7. So I have 7 du is equal to 14x dx. So this will allow us to rewrite 14x dx as 7 du. And now my integral is written entirely in terms of u. All right, we've completely substituted out the x variable. And now we'll integrate. So I'll pull 7 in front of the integral operator. I'll use a formula to integrate the hyperbolic cosine, which is the hyperbolic sine of u. And then I'll back substitute u for x squared. So we have 7 times the hyperbolic sine of x squared plus the arbitrary constant. So we have 7 times the hyperbolic sine of x squared, and we're given plus c. Right? Okay, so for problem number 8, right, we still made a substitution. Okay, now problems 9 through 14 deal with the hyperbolic inverse functions. And here again, the hyperbolic inverse functions, those formulas are found on page 198. So let's refer to those formulas. All right, so here we are. These are the derivatives for the inverse hyperbolic functions. Okay. So notice in our problem, we were asked to find a derivative for a hyperbolic tangent. Right, so this is the formula we would use. The derivative for the inverse of hyperbolic tangent is 1 divided by 1 minus x squared. So we would simply substitute our value for x into the formula. All right, so I'm going to go back. I just want to make sure I'm writing the problem down. So we have f of x, and again, this is problem number 9. F of x equal to the inverse of the hyperbolic tangent of 5x. And we're asked to find the derivative. All right, so keep in mind, we have a formula for the derivative for the inverse hyperbolic tangent of u, not for the inverse hyperbolic tangent of 5x. So here again, we're going to use the chain rule. We're going to take the derivative for the outermost function times the derivative for the innermost function. Well, no, I believe I'm misspeaking. Okay, I'm thinking about the derivatives. Here we're using those formulas. Right, remember that formula. I'm just going to write that here on the side. The derivative for the derivative for the inverse of the hyperbolic function of tangent x is 1 over 1 minus x squared. So keep in mind, this is the derivative for x, right? We have 5x, so we must make a substitution. I'm going to let u equal to 5x. So we have the derivative for u is equal to 5x. So du dx is equal to 5. So I have 5. And in my formula, I'm going to substitute x for 5x. So I have 1 divided by 1 minus x squared, but I'm going to substitute x for 5x. Right. So what I have here, this is I'm kind of writing this differently from when I wrote it the first time. This is the inside derivative, and this is the outside derivative. Okay, so for the outside derivative, we use the formula. Right, so now if we combine these two things, we have 5 divided by 1 minus 25x squared. Right? So since we are still taking a derivative, we're going to take the derivative for the outermost and the derivative for the innermost. So if I go back to have 5 divided by 1 minus 25x squared. So this is how you would find the derivative for your hyperbolic function, right? So number 10 is similar. We would use a chain rule, outside, inside derivative. 11 is similar. Now for problems 12, 13, and 14, we're asked to integrate our functions, right? And notice it in the directions, they tell us to either use the inverse of hyperbolic sine, or the inverse of hyperbolic cosine. Well, excuse me, they tell us to use the inverse of hyperbolic sine. All right, so let's take a look at the formulas. All right, so here are the formulas. So notice we must find the form in which our problem is given. So notice the form for the first one. In the denominator, we have the square root of 1 plus u squared. In the second one, we have the square root of u squared minus 1. For these two formulas, notice that we have radicals in the denominator. However, for this formula, I'm going to jot this down. We don't have any radicals in the denominator, right? So notice that this is the integral from 1 over 1 minus u squared. Du is equal to the inverse of hyperbolic tangent function of u plus c, and it's also equal to the inverse of hyperbolic cotangent u plus c. In the directions, we were told to use the inverse of hyperbolic sine. So in this case, we're going to use the inverse of hyperbolic tangent. All right, so just follow closely on this problem, because I'm going to do some weird sort of things before I make my substitution. All right, and this is problem number 12. I'm just writing the problem down. All right, so notice in the denominator, we don't have any radicals, so I'm going to use that formula for the inverse of hyperbolic tangent. But first, I'm going to play a trick on this denominator. I'm going to put it in the right form as 1 minus the variable squared. So I'm going to factor out a 64, And on the inside of the parentheses, I'm going to have one minus 1/8 x and that quantity is squared. And I kind of hear that there was something in the chat, so I'm gonna see what. Somebody said they can't see my screen. All right. Can everybody see my screen now? I'm sorry. I'm used to using my stand-up camera. So I'm going to just kind of go back on that problem. Okay. Okay, so just to go back, here I'm going to integrate dx divided by 64 minus x squared. And in the directions, I'm asked to enter the inverse hyperbolic trig function for sine. Okay. So I referred back to the formulas. And just notice that I'm looking for the formula that kind of fits my problem. You'll notice that in my denominator, for all four of these formulas, I have radicals. For this formula, 1 divided by 1 minus u squared du, I have no radical in the denominator. So this is the formula that I'm going to use. But notice my denominator is in this form, 1 minus u, okay, whatever u is, squared. So this is what I did. My intent was to put the denominator in the correct form, right? So notice how I played a trick on the denominator. But this is still one and the same. I just slightly rewritten it. Notice that in the denominator, if I were to distribute 64 times 1, that's still 64. If you were to square 1/8, right, you would square 1, you would get 1, you would square 8, you would get 64, right? When you distribute 64 by the second term, the 64s cancel, and I'm left with x squared, right? So I have that 1 minus x squared, so to speak. Right, my first term is a perfect square and my last term is a perfect square. From this point, I'm going to pull 1 over 64 in front of the radical. So now I can fit my formula using this denominator because it's in the form 1 minus 1/8 x squared. So I'm going to substitute u for 1 1/8 x. Right? Because here's what that will allow me to do. It will allow me to rewrite the denominator as 1 minus u squared. Right? Because I've substituted u for 1/8 x. Notice that in the numerator, there's still dx. So how we're going to substitute out this dx is we're going to go back to our substitution equation, and we're going to take the derivative with respect to x for both sides. So if we take the derivative for the left-hand side, we have du dx. We take the derivative for the right-hand side, we have 1/8. I'm going to multiply both sides by dx. And in order to solve for du, I'm going to multiply both sides by 8. And I have that dx is equal to 8 du. Right, so I'm going to substitute dx for 8 du. The next thing I'm going to do is pull 8 in front of the integral operator. I'm going to simplify 8 over 64, so that's going to give me 1/8. In order to evaluate this integral, I'm going to use the formula. I think my screen must stop broadcasting once I flip it over completely. I think what's happening with my screen is when I flip this notebook over completely, I think what's happening is once I fold this notebook over completely, it's powering down. All right, so I'm going to kind of go back on this. All right, so we're asked to integrate dx over 64 minus x squared. I factored out 64 in the denominator. Right, so notice how 64 times 1 is 64. 64 times 1/8 x squared, right? That gives me x squared. Next, I made a u substitution. I substituted u for 1/8 x. So that allowed me to rewrite the denominator is 1 minus u squared, right? Because I substituted 1/8 x for u. In order to substitute out dx for du, I took the derivative for both sides of this substitution equation. I solved it for dx, and I had 8 du is equal to dx. So I simply substituted dx for 8 du. And now I have everything in terms of u. Next, I pull 8 in front of the integral operator. All right, so I have 8 over 64 times the integral of du divided by 1 minus u squared. I simplified 8 over 64 to get 1/8. And now I'm going to use the formula to integrate 1 divided by 1 minus u squared, right? If I look at the formula, this is on page 198, 1 divided by 1 minus u squared is the inverse of hyperbolic tangent u plus c. So I'm going to simply substitute this integral for the inverse of hyperbolic tangent u plus c. I'm going to back substitute u for 1/8 x and I have my final result. So we have 1/8 All right, so we have 1/8 times the inverse. And notice I put my inverse symbol outside of my hyperbolic function. So we have 1/8 times the inverse of the hyperbolic tangent of x over 8 plus c. All right, so any questions about the hyperbolic section? Okay, I'm going to go back to the shared screen for just a second. So at this time, I'm going to stop the recording.